Hello everyone and welcome back. My name is Mr. Kovold, and in this video I'm going to be going over another calorimetry problem. So this involves a calorimeter, an ice calorimeter. So let's get into this. So a calorimeter that measures an exothermic heat, the exothermic heat of a reaction by the quantity of ice that can be melted is called an ice calorimeter. Consider a reaction in which 0.00400 moles of methane gas, CH4, is burned completely at a constant pressure in the presence of excess air. So meaning we have plenty of oxygen, so don't worry about that. The heat liberated from the reaction melted 10.7 grams of ice at 0 degrees Celsius. The heat required to melt ice, which is called the heat of fusion. Don't worry about the word fusion. Fusion is just a fancy word for melting. So the heat required to melt ice is called the heat of fusion, and that is 333.5 joules per gram. What is the change in enthalpy, or the delta H, for this reaction? So I think the first thing we need to do is write a balanced equation for the reaction of methane, for the combustion of methane gas. So first thing is we're given the formula CH4 gas for methane. That's going to react with oxygen. And as you should know, for any combustion reaction that involves a hydrocarbon, C and H, the assumption is that this is a complete combustion and that therefore the only products are going to be carbon dioxide and water. So we're going to end up with CO2 gas plus H2O gas or liquid. Doesn't matter in this case. Oh, oxygen is a gas. Okay, so now we need to balance. We have one carbon, one carbon. We have 4 hydrogens. We have 2 hydrogens over here, so we need a 2 over here. We have 2 oxygens here. We have 2 times 1 is 2. That's 4. So we need 4 on this side, so I need a 2 there. So now I have my balanced equation. So that's the first part. Now we're told that the combustion of this, the heat that comes from this reaction, is absorbed by the ice. This is happening in an ice calorimeter, so the assumption is that all of the heat released by this reaction is absorbed by the ice and melted. And so that's what we're going to do. And we found that 10.7 grams of the ice is melted. So we have the heat of the reaction, Q of the reaction. That's the heat released by the reaction. Q is heat. And so we know that all of the heat that's released by the reaction is going to be equal to all of the heat absorbed by the ice. So Q of the ice. So these are equal but opposite. So the heat released, that's going to be negative. Heat absorbed by the ice, it's positive. So we know this to be true in calorimetry. So that's all that's involved. So I'm going to move this. Now you can use this equation, that's fine. You could plug everything in. And so let's determine what the Q of the reaction is. So Q of the reaction is going to be equal to the enthalpy of the reaction multiplied by the number of moles. Because normally your Q of the reaction, your enthalpy of the reaction, your delta H of the reaction is going to be in kilojoules per mole. So you're going to have delta H of the reaction. And since it's in kilojoules per mole, you got to multiply that by the number of moles in order to get Q. Because remember, Q is heat. Heat is an energy unit. This is an energy unit per mole. So we're going to have to multiply this by the number of moles to get Q of the reaction. Okay, next, Q of the ice. What's Q of the ice? Q of the ice is the heat that's absorbed by the ice. So what is that going to be equal to? That's going to be equal to the heat of fusion, which is the delta H of fusion. Notice that this is kilojoules per gram, right? Let me double check that. Yep, kilojoules per gram. So notice, I'm sorry, joules per gram. Notice that we have joules, which is an energy unit, divided by grams, a mass unit. So Q is an energy, right? We want only an energy unit. In this case, we want joules left over. So this is going to have to be multiplied by mass. So mass in grams. So now that we have QR, the Q of the reaction and the Q of ice, we can now plug that in. Now, you can take this and plug it into this, leave it that way. Or what I like to do is move this over here. So I'm going to add Q of the reaction to both sides. And so this becomes 0 because plus and minus cancel out. And then this is going to be Q of the reaction plus Q of the ice. Now, I like to do it this way. You can just keep it as negative Q of the reaction equal to Q of the ice and plug everything in and solve it. It should work out the same. No problem. Okay, so now I'm going to substitute in these for Q of the reaction and Q of the ice. So I'm going to substitute Q of reaction and Q of the ice for these two. So Q of the reaction is this. So that's going to be delta H of the reaction, the enthalpy change of the reaction multiplied by the number of moles plus, and then Q of the ice I'm going to replace with this. So it's going to be plus delta H fusion multiplied by the mass of the ice. So now all I need to do is plug everything in. And so here, what we need to do is figure out the moles of the amount of, we don't need that. We got the moles here, moles of the methane, right? So we got moles of methane. We got the mass of the ice that was melted, 10.7. We've got the heat of fusion given to us. And so that's it. So now all we need to do is plug everything in. So delta H of the reaction multiplied by the number of moles, which is 0.00400 moles, plus the heat of fusion, which is 333.5. Let me double check that to make sure I didn't get that wrong. Yep. Joules per gram multiplied by 10.7 grams. Excellent. Notice here we have moles. Grams are going to cancel out. Grams are going to cancel out. We're left with joules. So now we just solve. So this is 0. So 0 is equal to delta H of the reaction. Oops. Enthalpy of the reaction multiplied by 0.00400 moles. This multiplied together is going to give me 3568 plus 3568.45 joules. So now I want to get joules over here. I want to isolate this. So I'm going to subtract 3568.45 joules on this side, and I'm going to subtract 3568.45 joules on this side. So I don't need this anymore, so I'm going to erase this. So So now I have negative 3568.45 joules, and that's going to be equal to this. This cancels out. I don't have that anymore. So it's going to be equal to delta H of fusion. Oops, reaction, not fusion. Delta H of the reaction multiplied by the number of moles, 0.00400 moles of methane. So now all I need to do is divide by the number of moles. So I'm going to divide this side by the number of moles, 0.00400 moles. That's going to cancel out. This is going to be divided by 0.00400 moles. Oops, I can write that better. 0.040. And now notice I have joules per mole. So now when I divide this, I'll get the delta H. So delta H of the reaction, the combustion of methane, is going to be equal to this, which is negative 892, 892,112.5 joules per mole. But normally enthalpies are in kilojoules per mole, so we're going to convert this to kilojoules per mole. And to do that, we're going to multiply, since it's joules over moles. So we're going to convert that to kilojoules. 1 kilojoules equal to 1,000 joules. We'll put 1,000 joules on the bottom. That's going to make joules cancel out. And I have 1 kilojoule on top. So now I'm going to end up with negative 892. And let's see. Yep. So the least number of sig figs is 3. So we're going to round that to negative 892 kilojoules per mole. And that, ladies and gentlemen, is how you solve this problem. So I hope this is helpful. If you enjoyed this video, if this helped you in any way, then by all means, like the video, share the video, hit that like button somewhere around here. Also, do me a favor, support the channel, subscribe to the channel, hit that notification bell. When you do, click all so you be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem that you need help with, I'm your man. If you have a topic you need covered, I'm your man. So just put that down below. Let me know. I would love to do that for you. Thanks for joining me and have a great day.